record myself at the same time as have um, Zoom and um, Rhino and Houdini open. It's going to be a challenge. Okay. All right. So the first thing is just a little background. Okay. Um, in terms of everybody ready? Right. Okay. In terms of fluid simulations, there are two approaches, and they are called the Lagrangian approach and the Eulerian approach. The Lagrangian approach is the one that people tend to think of, which is the particle approach, which is as though, every bit of water is being moved down the river and we're following the bits of water. And the Eulerian approach is as though you are looking at a piece of the water and the water is flowing by you. So instead of modeling the particles, you take a little bit of water and you describe the quantities of velocity or temperature or density that are flowing through it. And it turns out that the Lagrangian approach is not very effective because even though it's more intuitive, the reason is that it's very hard to keep the molecules the right distances apart from each other, unless you have billions of them. So this is what it is, right? The Lagrangian approach is particles moving, and the Eulerian approach is looking at the velocity in a cell. So rather than a particle moving, we only talk about the flow, the velocity of a particular cell. And the particles are moving through that cell, and we don't even think about them at all. You could imagine them like this, okay, superimposed. It's like looking at a piece of a river and just watching the piece of the river as the things go by you and accounting for the new velocity or the new temperature or the new whatever that's in the river. Okay. And that was pioneered in this article in 2003 by Josh Stamm, who was the developer for fluid simulators in Maya. It was called Real Time Fluid Dynamics for Games. And every single engine that is not, every single real time fluid engine for the most part is based on this paper. And they solve discrete versions of the Navier-Stokes equations, which I will go through with you, not today. And the other innovation in these simulations has to do with this idea, which is that you would imagine that what you would do is that you would calculate the velocity in a point, and then you would just run it forward one time step. Okay, so it's the reason I'm doing this, by the way, is it's a little important to have this background information to understand what's happening when you look at a simulator. They're done in time steps. Okay, so there's like a cell here, and there's a velocity here, and we know a time step, which is delta t. It's like a millisecond or something like that. And we multiply the velocity times the time step to find where the new velocity would be. Okay. That is called, that's what's happening. So in every one of these simulators, there's two constraints, and the two constraints are delta t, how small is the time step, and h, or the size of the grid cell. Okay. And this approach, by the way, of finding a point, finding a value, and moving it by the velocity times the time step is called forward Euler. Nothing to do with the other Eulerian, different term, forward Euler. And what's weird, okay, is that actually forward Euler deteriorates over time, because you can imagine it would be very hard to find the correct velocity again at the center of the grid cell after you've taken a single time step forward in forward Euler. I'm going to go through this again in detail, okay? But the innovation is called backward Euler. We pretend that we're in the future, we look back in time, and then we figure out where we would have been. Okay, that we'll go over it in detail. The point is that this particular article is the innovation. Okay, the other thing you have to understand is these two concepts. Okay, so forget what I just said about forward Euler. The delta t and the h. Okay, the grid cell size and the time step, and then you need to know the difference between a scalar field and a vector field. Okay, a vector field has a vector, 3 numbers at every single point in space. They're represented like this. And a scalar field just has a scalar value at every single point in space. Okay, so there are two kinds of fields. There are scalar fields and there are vector fields. So a density like smoke or temperature is a scalar field, and speed or velocity is a vector field. So we need both. So yeah, okay. And so there are 3 parts to every single fluid solver. 3 parts. There's a source, okay, and that source is the starting condition: density, temperature, velocity, and some other things. But mostly these. Density. Why are we talking about density? Just smoke. For some reason, these things have a history of representing smoke. Okay, so density means smoke. Doesn't have to do with anything with the density of the water or the air. That is the uniform density. Density is smoke. Temperature, how hot it is. Velocity, how fast it's going. Okay, so you input your starting values, and then there's a solver. And the solver does the following thing. It does what's called velocity self-advection, where the velocity updates itself to its next position. Then you add all the forces: turbulence, disturbance, viscosity, buoyancy. And then you do something called pressure projection, which is to correct for the errors that get engendered in that process. And then sometimes there's like new velocity coming in or new temperature coming in, which is like a heat source or a heat sink or wind. And you source those back in and you add them to the values. And then you do the whole thing again for the next time step. And then the third part is what's called the target field. And these are where all the values are stored. So there's a source field, and then internal in the solver, there's always a set of variables that are stored. And these variables are stored for every single solitary point in space. So like there's basically, a giant grid, and it stores temperature, pressure, and velocity at every single cell, runs through every single cell and updates them in all of these steps for every single time step. Does it again and again and again and again and again and again and again. And so you will see these 3 things in every single setup for every single simulation. Okay. Before we do Houdini, I uploaded something else. So I have a simulator for Rhino, which I wrote, that I will go through with you. How I wrote it. And then we will also use Houdini. And they are the same. They're fundamentally identical. Houdini is like an elaborate user reconfigurable version of the exact same algorithms that I am using, because they are based on that paper and on the innovations that have come since then. Okay, so if you open up the file that I put on the server, which is called, it has a kind of an unfortunate name. I think I didn't rename it. It should be called like Air Diagram 4 or something stupid like that. And then it's under on the canvas. Here it is. Not on Canvas, on the Google Drive. Put it on the Google Drive. I can share that again if you guys don't have it. But this is there. So we have a Rhino version and we have Houdini, and we can use both. Okay. So the Rhino version is right now it's 2D. If there's time, we maybe will extend it to 3D together. The principle is identical, whether it's 3D or 2D. It just you need to make a few little changes to the lines of code. Okay, so that's it. And this thingy here is this. Okay, it's a whole lot of code. Okay, but let me go. It's actually quite easy to use, I hope. And it has the same parts. Okay, so you don't need to know Grasshopper to use this. I promise. It is not a Grasshopper game. Okay, these are the source fields. Okay, so this little thing up here, which I want to write with you guys probably, is a whole bunch of points. Okay, so it's like it's a grid. And if you change the inputs over here, the 80 and 120, and this is the H. Okay, so this is what plane it's on. This is the H. That's the size of the cell. So if that gets littler, it'll be very slow. And this right here is the number of grids in the cell. Okay, and if I and then so if I change this, if I put like a thing in here, I put like some closed polylines in here, and this is let me make this a little smaller so it's not as slow. There's change the bounds of the simulation. Okay. Correct. So that is a very nice, easy little piece of code that I may teach. I probably go through with you in detail. Okay. And then these are the source fields. Okay. So basically, this is what's called a signed distance field. So it is the Houdini has the same things. Basically, if I put some curves in here, I don't need the hatches. They're just there for display. There's like some closed boundary curves. Okay. So if I take these curves and I put them in here, I go set multiple curves. And then I click this button, which resets the values. What it's doing is it's creating what's called a signed distance field. Okay. And that is it assigns a number for the distance from the object. And there's negative numbers if you're inside the object. And that is how collisions are done in simulations. It knows. So if I plug this, if I take this and I plug this field out here into into my little display over here, plug it into my little display over here. No, what are you looking at? What are you looking at? It's not on, so it's not. I don't know what you're seeing. Let me look at it with you in 1 second. Um, okay, so like that is what it's creating. Okay, it's creating a signed distance field, like of a gradient of how close you are to the object. It'll work in anything. What's this?
I don't know. Like, what do we click to like make it work?
Yeah, I'm gonna. That's what I'm going through right now.
Oh, okay. There is already something plugged into there.
It's okay. So like this, I'm just telling you these are the sources. Okay, so before you do anything, before you can run any simulation, you have to load the sources. Okay, so and we will do the same thing in Houdini. We will have to load sources first. So this is the collision source. Okay, there's the temperature source. And this is probably something else that we don't need. This is some other idea I had. So there's the temperature source, and there's the collision source. Okay, temperature collision. And it's doing that. We're not going to deal with temperature yet. Okay, we're just dealing with the collisions. So we can ignore the temperature for now, and we can just deal with the collisions, which is this. So if you don't have a collider, nothing is going to happen. It's just wind is just going to go straight through. So this you need to put in closed curves. Go set multiple curves in here, and then you check the button to evaluate. Okay. And then there's a kind of an issue which I hope I will solve, but this is the issue, okay? Which is that the simulator, this entire thing will run in 10 milliseconds. However, the loading of the display of the variables into Grasshopper, every single frame will slow it down by multiple orders of magnitude. So Grasshopper, we need to have a data dam, okay? Which means after you start the simulation, you need to, before you run it, you need to dam the input of the data so that it's not continually loading the data every single time. Okay, so this should be on false to begin with. And then what we need to do is look at these options over here. Okay, we need to set the options correctly. So this is the button that will reset the simulation, start it over again. These are coming in from somewhere else. They're the size. Okay, so we can ignore those. This is the delta T. So this is fine. It's kind of irrelevant. This is the delta T. This right here is the speed of the wind. Okay, coming in from the left. So right now I have it set to 10. That is the speed of the wind in the other direction. So I have that set at 0. This is the temperature. So I have right now all the temperature set at 0. And this is the other one. So okay, so there's two kinds of values here. There's these things that say U start, V start, S start, temp start, and then there's in U, in V. So in smoke. Okay, so the start ones are the initial conditions, and the in ones are the ones that get input on every single frame. So the way I have this now, if you look at it, is I'm starting with the velocity of 10 in the U, and I am starting with a velocity of 0 in the V, and then I'm inputting 10 new U every frame. So basically, it's going to keep a constant wind blowing in from the left by resetting the entrance values to 10 on every single delta T. Okay. Then this is just the density of air, so that never needs to change. And then we have remember I said there were all of these, there were the update step, the forces. So the first step is the in-sourcing. Sources. And then these are the forces. So the first step in every simulator is you source in the value. The second step is you add back the velocities. That's done internally. And then the third step is you update all the velocities with the input forces. Gravity, buoyancy, viscosity. Am I making sense? Okay. So these are the forces. So you can ignore this vorticity right now. Vorticity is a very interesting thing. Okay, it has to do with the fact that because it's a grid, we are averaging values we are sampling values in order to fill in the grid. And so that means there's a blurring effect over time in every digital simulation where it gradually loses energy. And so in order to counter for that, you insert some spin back into the system. So this vorticity is a artificial spin inserted back in order to keep the energy in the system from dissipating over time in an unrealistic manner. Gravity is gravity. Viscosity is viscosity. Viscosity is how sticky the fluid is. Buoyancy is how much lift there is from temperature. Okay, and that has to do with the fact that very few simulators use a realistic model for temperature. We use a kind of an approximate buoyancy model, but these will not work unless you have an input temperature. So we're ignoring those for now. Okay. And then there's diffusion. Diffusion is just like every neighboring velocity picking up some of the neighboring velocities. Like you know, the way like if you you hit water, eventually it smooths out. And then these are more controls about temperature. Okay. Then there are the boundary conditions. Okay, so these are the boundary conditions. So this says it is open on the left and the right and closed on the top and the bottom. Okay. These are parameters that have to do with the simulation. And then these are all the options for what you can turn on and off. So these things turn on and off various aspects of the simulation to make it run more quickly. So this is on noise. I have noise off. I have fancy collisions on and off. I've got diffusing the velocity off. I've got advecting the temperature off. I have some other yes.
It's in front view, like we're looking at.
You can change the plane that it's in, horizontal or vertical. It cuts a cross section through the project. It's a cross sectional, like this is like a plan, but it doesn't matter which direction it is in. We could change the plane that it's on to horizontal. Yeah, so the buoyancy and gravity operates just up in the two-dimensional plane that you set it in the way I've set it up. Like, so if you're doing a plan, you will never turn on the buoyancy. Yeah. And if you're doing it vertically, you will turn it on if you're simulating with temperature. And if you're not, you'll just leave it off. And so these things here are just, so this is on diffuse the temperature, on advect the temperature. These are off because I'm not using temperature. This is a different temperature model. And then I don't remember what these are. There, the vorticity, I have it on. The gravity is off. Smoke is off. And then these are the out parameters, okay? So this is what comes out of the simulation. These are the fields that we get out of it. By the way, it works the same exact way in Houdini, so it's kind of important. Mine is like a dumb version of it. So then, like, these are the fields that you have options for what you turn on and off, right? For different kinds of simulation. And then these are the fields that we output. So internally, all those fields are there. They're all stored inside, but outputting them takes memory, slows the computer down. So we only want to output the things we actually want to look at. So you can out the pressure, you can out the velocity, you can out the temperature, and you can out the curl, or something else, and then you can also out the streamlines, okay, which are those lines in the simulation. All right, so let's see if it works. So if I load that, and then I'm going to disconnect this this gradient over here, turn this thing displays the gradient, so I can turn that off. My whole thing is set up. I'm going to click this, and then I'm just going to click this button. Okay. And this is running slower than it needs to, because if I turn this off, it'll run faster. So that is wind blowing through the building and arriving at a state of equilibrium here. And I can change the streamlines down here. These are the controls for the streamlines. So this is the length of the streamline. This is the length of the streamline here. If I make that longer, they're going to be longer. This is the number of streamlines. And this is the thing that updates the simulation. So if I hit this pause, it'll stop. Okay. If I want to restart it, I just click this button again. I have to turn this back to false. Click this button, turn it back to true, and start it again.
Can you explain what the data DAM does again?
Yeah. So the reason for this, and I may, if I were to package this up in Visual Studio, I'd be able to get rid of this. But because I've left it open, I can't think of another way to do it. And what's happening is that every time step, all the inputs get reloaded into the Grasshopper thing, even though we're not using. And that it's loading thousands of values every second. And so if I just dam the data from going through, the simulation will run faster.
Oh, but it doesn't. If the data DAM is on, you can still run the simulation.
Yeah, it just will run faster. It just goes faster.
So the data DAM can always be true.
No, when you load the data, it has to be false. When you load the data in, it's set to false. And then you turn it to false, you click this button, then you turn it to true, and then you go down and turn on the play button.
What do you load? Which button do you click to load the data again?
Yeah, so there's a button here. This thing at the top that says reset.
The load.
That loads the information. Every time you want to restart it, you reload the information. Yes. Let me look at it.
Get to the blue.
Well,
Well, I had the error before as well, but somehow it just fixed itself after a while.
let's zoom out. Let me look at it. I think it's because you're not. You don't have the out for the color.
Oh.
You need to turn out pressure or out velocity or something like that. Oh, so okay, so let me show you what that is. Okay, so like basically I should have cleaned this up a little bit. I apologize. I keep tinkering with it. Okay, this is the gradient display. Okay, so basically any value you plug into here will get displayed in a gradient like that. So if you wanted to display a value, you need to take the temperature, or this is the velocity here, or this is the there's the pressure. So if I wanted to display the pressure, I need to take the pressure and connect it to this thing here, and then I can turn this on like that. Let me turn off the streamlines like that. Did that work? Yeah. You have to basically, like, these are the output parameters. These are the output parameters. So this pressure here, it goes down into this this is the gradient creation area. If it's not working for you, I promise you it's like a little thingy. I will fix it. If when I let me just save this one again and upload it. Okay, so this is the updated one. So this I'm gonna just do it one more time. Okay, so this this is something we will not use unless we have an individual project that we need. This is the temperature, so that's much more complicated to source, and I'm not going to do that now. This is the update for the sign distance field. Then you got to check this to false. And then you go over here and you click this button. And then you go down here and you hit play. And if you want to change a different output, you need to click the correct output on, and then you need to go over here and find the output and connect its values into the gradient display, which is right here. So the reason that velocity is a little different, okay, is because the velocity is not really a single velocity. It's actually a velocity in X and a velocity in Y. And so what you would need to do is actually connect this value here in order to display the velocity, and then turn on out velocity.
Where is the distance, the update the distance?
The sign distance field. That you got to put curves in here, and then you got to click this button that says evaluate. And then that is pumped into this data dam. And then you go up and reset the simulation. Let me like walk around for a minute and make sure it's working. Okay. Let me look at it. How is that? Who's having problems? You're having problems. Okay.
It's getting worse. It's no pressure.
Yeah, we're selected.
This has got to be false. The way you start the simulation.
No. This. Now, yeah.
This button is this thing here is what goes into the data dam. Yeah. The stream, they're showing the streamline.
Wait, can you explain it?
And that basically the streamline, okay, what it is it's like every point it like extrapolates into the future where it would go.
Can you explain how do I connect the different colors to like check?
Yeah.
Now I don't know what it's showing. I don't know what the color means.
Yeah, it's like coming out of this. So like
Now it's showing pressure.
it's showing pressure is going in there. So if you wanted it to show velocity, it would be this thing from this length over here.
Oh, okay.
And then you would have to go down here and turn on the out velocity.
Oh.
Yeah, because unfortunately the velocity one of the things is about these kind of simulators, the velocity is not stored as a single value, it's stored.
It's like bundling. So you're sort of like deconstructing this.
It's got a velocity X and a velocity Y, so I'm combining that to show the magnitude.
Oh, you're constructing the vector. That's kind of annoying. I see. So you're constructing this vector and then you're getting the directly show them. Not like the vector like.
Yeah. Mhm.
Okay.
It looks like you might be missing a wall over that. Yeah, it's blowing through the wall.
Oh, I think I just said that.
Yeah.
Oh.
Anybody issues? You have an
Is
issue?
it working yours?
Yeah, it's working.
Do they know what was the order?
Yes, I remember. Like
My first time with the last for something.
it's like so my let's see. So do you do anything beforehand? First, have you set the curves yet? Okay, so first this is the colliders, right? You first have to get the curves that will collide with the fluids. So you first select like the curves, or just select the cell curve. Cell curve. There we go.
Why am I missing those?
You set multiple curves like this. Now it's like these curves are stored inside this component.
Okay.
And
Then you did it with command? Or-
oh no, I first selected these
Okay.
curves, or you can like you just set multiple curves, and then you.
Okay.
It doesn't work for some people though. That and you like that. And then, okay, now it's like now the next step is you gotta so stated first gotta evaluate it. You evaluate, right? So you double click this button.
Oh.
Evaluate what means?
Evaluate just means you like start the simulation, kind of. And now you have to now you click reset, right? So you run it like this now. Now it's running. And to make it run faster, there's a data dam, you have to make this true. So it will like make it run faster. Because otherwise it'll keep resetting every second. Now it's like running. Why is it not running though? Yeah, now you just click play and it'll work. That's all, yeah.
Okay, so the order is selecting the current and putting it into
The
the,
curves thing. This curve exactly.
and then
And they evaluate,
evaluate.
reset.
And what about this one? Because I've seen that sometimes. It's
Data dam just means dam is like it's like blocking the data, right? So you want to
Okay, but
you have to when you reset it, it has to be false.
You reset, so we have one.
At first it's false.
Okay.
Data dam is the last step. You make it true in the last step so that it doesn't keep like doesn't it's like when you click reset, it's gonna take all the initial variables and put it into the simulation, right? But if you if this is false, it's gonna keep updating the variables every second. So if you make this true, it's gonna block the data from flowing in, and it'll just run the simulation directly itself.
Okay.
That's why you keep this true in the beginning. But if you want to reset the whole thing, you gotta like make this false and then like
You
reset
say
it
you want to
back
understand how it works.
like that. Like when you change stuff.
Yeah,
Yeah.
I'm
That's
not
the
like.
correct feeling.
So.
So I will explain.
Okay, and now what it's representing is
Like, the way to show is like well, you have to see like the way to find out it's like you find like this is this thing, right? So what is the thing that's going into this? It's all this line. So this thing is this. So now it's representing pressure. You want to represent like the vector velocity. If you get this first positive. Starts lag now.
Like,
Yeah. So you first pause it and you do. So this is kind of messy. I have to like. So you have to plug it into here. Right? So you have to get the velocity. This is the length. This thing.
Okay, it's with the length, not with this one, right?
The reason Carl explains it is because. Anyway, the reason is because this thing doesn't output like a complete velocity. It separates the velocity into X and Y. So you're gonna this component constructs a velocity based on X and Y. So if you get this plugged
So
into
the
that.
purpose of this guide is so that we can make nice, cool images and that you can have something to work on, test your drawings with to make it fun. there's two purposes. One, so it's fun because working with Win is not fun. And the other purpose is because it's a broken down version that we can construct ourselves, so we can understand exactly what's happening in the other software. Okay, so those are the purposes.
I don't know if you do that way, so maybe do
Yeah.
it. You said it.
Okay, so very ready.
Then, and now it's outputting velocity.
Okay, so in order like to clean all the data,
Yeah, Carl, other
Yes.
question. Every time you change the thing you're displaying with the color,
You don't have to reset it.
you don't have to reset it.
No, you just have
Oh.
to change what's
I
on.
see. Okay, so I guess that was a ridiculous step. You didn't need to reset
because
it.
the data is already stored.
Yeah,
So
it's just deciding whether it's outputting.
So you only need to reset it if you change the in variable, like the
Yeah, or if you want to start the simulation again. By the way, the run time is there too. Like if you look at it, it runs right now like uh um it runs only 2,000 times.
Oh, it
That's
is-
what that button
it
is.
stops after 2000.
Yeah, if you made that higher, it would run for
Is it
longer.
2000 like ticks? Like what is how long is it tick?
2,000 updates. It will
Oh.
update 2,000 times.
How
It's a very good question. So if you go to Grasshopper and you go here, you go to preferences, and you go to the widgets, and you go down here and you click the show profiler widget, that will put the milliseconds that it is taking to update down here. So it depending on how many options you have on and what you're outputting, it will run
can you
faster or slower.
manually like bottleneck that and fix it to like cap it to like a variable? Like you want to run it like every 100 ms.
So I mean, ideally, it would run at like 30 milliseconds, I think,
Okay.
but it won't, and Houdini won't either. None of them ever do.
It's not like you kind of like cap like the FPS.
It's just like it's just running like not in real time.
Okay.
And so if we wanted to run in real time, we'll have to bake the simulation out.
What do you mean it's not running? Dude?
Like
not-
it's updating only when it finishes. So like actually that's a really good point. So like the time between one frame and the next frame as it's displaying on the computer is not the delta t. The delta t is the time step like in the mind of the computer, which has to do with the resolution. I don't know how to say it. It's complicated. Like the delta t just has to do with how far I move a point every update. Like,
Oh.
but because the computer is slow, the simulation slows down. So it's not running at the speed of the actual thing.
So delta t just determines like how big each velocity arrow is.
Yeah, that's right. It determines how big, it just like if I have a bunch of points like this, point, and this one has a velocity of 10, and this one has a velocity of 10.2, and delta t is 10, then this point is going to get moved 100.
Oh, okay. So if that's the delta t is increased like 10 times, then the
Delta
velocity-
t is just telling me like basically how little do I sample. So like it's telling me like am I sampling here, or am I sampling there, like
Wait,
you know-
that's delta t? I thought that was h.
H is how big the cell is. So there are two versions of resolution. One is the time resolution and the other is the spatial
Oh, but I
resolution.
thought okay. No, maybe I'm not understanding it. I thought the time resolution means like the greater the delta t, the least frequently you sample in time.
That's right.
So
That's right.
If you sample less, it means that each time the arrow will be longer.
That's right.
Okay. And it's like it scales linearly. So if delta t is like 1 second versus like 0.1 seconds, and delta t is 1 second, the arrow will be 10 times longer.
Correct.
Okay.
And you're right to question whether it scales linearly. And there are models where there's two versions, one where it's linear and one where it's not linear, where it's like a cubic function.
Oh.
I have to say, the point is only that it's broken down by cell.
Okay.
And I will go through, like, we will go through it very slowly.
I see.
Like, I want to actually go through it with you,
Yeah.
like in great detail.
Mm,
Like, I
very
want to
impressive.
draw it out with you on the board. So like,
Yeah.
your questions are good, but like, you don't have to absorb how the simulator works from what I said now. I will go through that with you. But like, if you like, it is also it's also here for you, okay, for all time. If you ever become a coder, there it is. Okay, open source, there it is. Okay. All right. So we will not go through every single part of this, but we will go through the crucial part.
Did you write it in C# natively?
Yeah.
Okay. So you just wrote it in C# first, and then you baked it into Grasshopper.
Yeah.
Okay.
Um uh so the thing with the delta T, you're correct, is how frequently do you sample?
Yeah.
And in time.
Right.
And the thing with the H is how big are the cells?
So when the cell is bigger, it doesn't affect the length of the arrow. So
That's right.
It just averages those.
That's exactly right. It's an average of how big the cells are. Yes.
Okay.
Your intuition about it is completely spot on.
So in real life,
Yes.
you would just make not infinite, but like you would just the cell would be the resolution of the air molecule.
That's
in real
correct.
life.
The cell would be the resolution
So
of.
calculus can be applied to it.
That's right. The cell would be very, 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 very tiny.
Not
And in fact, there is a scale that people have. It's called like the Humboldt scale or something. That's the scale it has to be in order to be physically accurate.
oh, like if you do like 100%, or not 100%, like extremely accurate simulation.
Yes, we know how small it has to be, and it is beyond our computing power.
Oh, like okay. You need like super, not even super.
No, you can't do it on a supercomputer. You need like, the Earth.
Turn the whole Earth into a supercomputer.
Yes.
Like a.
That's right.
Jupiter.
Like it would take like months to run like a short simulation on a supercomputer.
Feel like milliseconds.
Yes.
Take months.
But that doesn't mean that we can't get accurate data. That's just if you were to try to do it in the dumbest way possible, then that's how long it would take. Okay. Like if you were to just do it like the universe does it, rather than doing any approximations or things like that, right? Okay. All right. So this is our own private version. It's here for two reasons. It's here. The reason I'm doing this today, by the way, is people ask me questions about what kind of models do you need. So in order to do that, I got to show you what we're going to be using. Okay. And that's why I want to go through some of the Houdini stuff too, so that you know what you're putting the model into. Otherwise, you will not know what to model, right? And then after that, we will go through in greater detail how it works. And you can, cut a cross section and put it in there, and it's hilarious and funny and fun to look at, which is what architects like. If we're going to use wind in our lives, it has to be fun. Otherwise, we'll just forget about it. Okay. Okay. So this is the same. This is the source, the simulator, and the outfields. And the infields, by the way, I want to show them to you just so you understand what you're looking at in the code. There they are. These are the things. This is where what is stored permanently. The U velocity, the V velocity, the temperature, the smoke. These values are permanently stored at every cell. Okay, so in Houdini, it'll talk a lot about the field. And this is what it means. There's a list of numbers, one for every cell stored in the memory. That's a field. A field means a big list of numbers. It means an array, okay? So in computer language, I don't know how many of you are computer people, but what it means is This is a number. This is a scalar, 5. That's a scalar integer. This is a scalar float, 5.0. That's a float. Or a double is a real number. This 5.0, 2.1, 3.1, that's a vector. And an array is a long list of numbers. Okay? And you can have an array of vectors also. Okay? So, and then the other one is a bool, which is a true false. Okay? All right. Is everybody okay? You are with me? Excellent. Okay. Now, I'm gonna switch gears. Okay, and we're gonna look at Houdini. I'm gonna try to go slowly, and hopefully, that'll be useful. Okay, so I just put in this PowerPoint, which you'll have, I just put a few of the commands, the key commands that I use a lot. Okay. And basically, okay, here's the interface. Okay, this is the interface. It's Alt rather than whatever it is on Rhino that you have to use to do this stuff. Okay, so it's very annoying. You always, yeah, it's Alt, middle, and pan. Okay, and then there's the this is the main viewport window. This is the most important thing over here. This is this palette where you have all these nodes. Okay, this is Houdini is like long chains of nodes connected together. So it looks a lot like Grasshopper, but it's not at all the same. It's like long chains of nodes connected to each other. And you can break these nodes by, by holding Y and doing that. Or you can, just select them and delete them. And you can connect them to each other. The idea behind Houdini is that it's about building little tools for that do little like simulation. Okay, so this is what they use to do like visual effects of like fire and smoke and water and for movie studios. Okay, so there are, and then the other window you will use is this. This is called the parameter window. So this has all of the controls that of any particular node like can be adjusted. Okay, all the little buttons that can be adjusted for the nodes. By the way, it is a vast program, and most of it is not necessary for what we are doing, and most of it's not necessary at all. There's a lot of history and legacy built into it, like a lot of things that have been updated and updated and updated, and little different tools. We don't need most of that. Okay, so it seems cumbersome at first glance, partly because the logic is a little different than Rhino. But it also, you don't need to learn all of the things that exist in here. Like, for example, all these buttons up here, like never click them. Okay, they are gone. Okay. And then if you ever mess up your screen, you can go here, reload current desktop, and it will set it back to the normal thing. And then these are the other, so sometimes this technical one here has a few more things. This tree view is also useful, okay? This is all of the nodes in the scene represented in another way. So the only things that matter are the view here, the tree view, and then this palette here with all the nodes and the parameter window. Okay? The tree view is like right here. Or I think you can go up here, window, and I think you can turn it on up here. Okay. Um, okay. So the next thing about Houdini is that there are contexts. Okay. So there are like, this is what's called like the OBJ level. It's called the OBJ level or the object level. And that is in the geometry context. Okay. So if I go to my PowerPoint here, like oh, let me say one other thing first. So when you want to create these nodes, you hit tab. Okay. You hit tab and it brings up all the nodes that you can create. Okay. And we will never use any of those. And if it, depending on where you are, it brings up different nodes. So the tab is context dependent. It brings up different nodes depending on what you're over. Okay. So like we are right now in a particular context. We're in what's called the geometry context. And so the nodes that I can create in the geometry context are different than the nodes that I could create in other areas. Okay. So like I want to just zoom ahead a little bit. Houdini is a little bit like Inception, okay? There are levels. There are levels, and then there are things hidden within the nodes, and then there are levels within the nodes, and then there are levels within the nodes, okay? So if I click on this node here, it opens up like another one. And it just goes on and on and on forever, deeper and deeper and deeper. Nodes inside of nodes, inside of nodes, inside of nodes, okay? And that is both frightening and good because it means that whenever you get a node from Houdini, like if I go here and I load the Pyro solver, okay, and I put it here, if I right click and I go allow editing of contents, and then I dive in here, it'll expose the way that the Houdini people created it, okay? And then within here, by the way, there's another one and another one, okay? It goes on forever. If you right click on it, it opens the thing, okay? You don't need to do it. It's overwhelmingly complicated if you do that. I'm just saying that it's built of the same nodes that you will build things. So all of these graphics software is very open-ended. All like Maya is like this too. It's built of its own self. Unlike Rhino, which is a set of packaged tools, it is made of itself. Like it's the display you're looking at and all the tools and things you can click on, you could recreate within the program. Okay, so all right, so if you there's a few more things here, like there's different display things. Okay, so if I were to like let me go in the OBJ level, okay, I'm gonna delete this for a second. In the OBJ level, if I type here and I type torus, and I place it here, there's a torus, okay? And if I type S, I can select it. These are the different levels of selection up here. Yeah. If I type S, it allows me to select things. Yeah, and then G zooms to the thing that I have selected. And so I'm in the OBJ level here, okay? And if I dive in, you basically do nothing you basically do nothing here in the OBJ level. All I do at the OBJ level is I create a container. So usually what I would do is I would not make a torus. Usually what I would do is I would just make a geometry node. I would just make a tab. I press tab. Or what like I'm already in a geometry, see? Like I would make a geometry node like this at the OBJ level, place it, and I would rename this something like smoke simulation. And then I would go in that. And that is because you double click on it to go inside of it. And that is because the way it works, okay, is a little confusing. You basically make little separate parts of the scene. Like if you're making like a firestorm and there's a plane and there's a snow, all of those things are separate effects that you edit separately because they're too memory intensive. And you don't even look at the other one while you're editing it. You only import it in as a reference with like some wireframe geometry. And then at the end, you combine them all in a scene and render it in. So the reason it's set up like this is because like now I'm like within an effect. Like that was the level where all my effects were stored. Now I went inside and I'm in my smoke simulation effect. Okay. And then within here is where I would make stuff. So here I might make like a cube, place it here. And then like I can change the parameters. You know, I can scale it, make it longer or shorter. If I want to move it, I can either move the center point here or I can create a transform. And a transform, I don't know if you guys know this, but this is always what Rhino does as well. It just is hidden. It appends a transform to an object. So the other thing is, okay, you will not see anything other than what has this blue flag. So the blue flag is like the thing you want to look at. It's the thing that is exposed. And it's the last thing, in the chain, basically. And so if you want to look at something, so for example, if I click on this and I hit enter, if I turn this on and I go over here and I hit enter, I get my gumball and I can move this. But then if I go back here and I turn the flag on here, I'm looking at the original cube.
How do you wait, sorry, can you repeat that?
Yes. I have it selected and I went over here and I hit enter and then I have the gumball. And then if I want it to go away, I hit escape. And this right now, I'm not seeing this. In order to see this, I have to go turn on the blue flag. We will work through it together. It will be okay.
Going to ghost of the other.
Okay, so one way that I could animate this thing, okay, is if I put into this translate here, if I put an expression, $T, and then I go back here, that is linking it to the time.
Wait, sorry, what do you click after that? How do you play again? Oh, just
Yeah, I put $T in the X of the translate. If I divide this by 5, it'll go slower. $T. So $T is the time.
Transformation that you made as a flag.
The time in milliseconds.
Clearing that action that you did. The thing that in there. Box and then there's this.
Yeah, so that's the frame. So at the bottom, that's 240 frames, and this is probably in like 28 or 30 frames per second. So the time is based on the frame rate. And you can also do $F, which would link it to the number of frames. So if I do $F, it's obviously going much faster.
it's like feeding.
Okay. And then, but that's not typically okay the way you animate things. It's just a little helpful thing. Okay, I'm going to make a sphere here because it's a little more helpful. Okay, I'm going to make a sphere. So there's two kinds of spheres. There's sphere polygon and sphere primitive. A sphere primitive is like just the point in the middle. A sphere polygon is the one you would usually make. Okay, so here I can drag up the rows, I can drag up the columns, make it more detailed. And then I wanted to show you this. If I click this button here, it turns on all the points. And if I click this button here, it turns on all the numbers of the points. So the reason that Houdini is able to do simulations is because every time you put a node in here, it acts on an array of points, basically. It acts on all of the many points. Okay, so let me see if I can okay. And then also you can turn on the normals like that. Okay, there are the normals. Okay, so this is the OBJ level where this is the geometry level where you create geometry. Okay, and then let me make sure that I'm going in my right order here. Yeah. All right. Then there is something else, okay, that are called they're called VOPs. This is so the first context is the geometry context. It's what's called SOPs. Okay. And then there's also there's the editing of things, basically, and that's called VOPs. It's a different context. Okay, so basically everything you create has lots of attributes. So I think if I look at this object, if I go to the geometry spreadsheet, there are its attributes. Okay, it has a px, a py, a pz, all those points.
How do you go to this screen again?
It's this geometry spreadsheet up at the top. And if I want to, like, let me see if I can do this. If I want to edit this, what I need to do is I need to go like, I need to create all of these other things, all of these nodes are like pre-packaged ways of editing something. But the way that you would actually edit something, typically, the way that people always do it is either VEX, which is Houdini's native scripting language, or it's VOPs, which is the graphical version of it. And you enter that by doing an attribute VOP. Like attribute VOP. So if you make an attribute VOP and you plug this into the first thing, so this is in the geometry. I'm in at the object level. I just created a geometry node to contain everything. Then I went in that. I created a piece of geometry in SOPs, and then I would create. Then I would start editing it and making a chain there. Okay, so this attribute VOP is like the way of editing things. Okay, so if I go in here now, it exposes the parameters for me. Okay, so what I could do is I could do something like, now what's weird, this is what took me a very long time to understand. Okay, essentially this thing already has, it's not like Grasshopper. It's not Grasshopper. This thing already has a bunch of attributes. And they're already there. And you just adjust them. And then like within the attribute file. So it's like the object possesses attributes. And then inside of this, you just make changes to them. And then you re-export them to the same exact list of attributes. Like you're overwriting the same values. So what I could do here is I could do like I could do like a displace along normal, and I could do a curl noise. We're not going to do this, by the way. I don't do this ever. I'm just trying to do it now to show you. I could do a curl noise. I would take all the positions, pump the positions into the position of the curl noise, and then I would pump the noise. I could multiply. Yeah, I'm putting the noise into the displace along normal, and then the displaced P here. And then I could click on this noise and I could go over to here and I could go, I'll do this again if it works. Go create input parameters. Then I can go out of this and I would have all of these input parameters. And if I adjust this, if I turn this on, yeah. Okay, so like so what's happening is something very what's happening is that it's doing a lot of operations all at once. Okay, it's taking every single p-value and it's using those as the source for a noise function. And then it's displacing things along the normals by the noise. And then it's outputting those things again to the same p-value. So it has a list of p-values, doing a bunch of shit to them, and then it's overriding the p-value with itself. I mean, that you would never want to do that, but I'm just trying to illustrate how it works. Let me see if I have a good one in here.
Oh, it doesn't work for you. I didn't do that though. What is yours?
Like if I had done this, I'm gonna do it on a grid instead. I'll do it on a grid.
Oh, if you drag this to it first. Yeah. I know. You have to show it. How do you adjust the slider though? I don't get it.
Oh, it's just unit.
Where? Where do you do that? Yeah, that's right. What else can you do?
Right click. That's not.
Where? This one create input parameters, and they want you to do with that. What do you do? Like that?
No, it's not. It's called.
Yes. On the outside? Yeah. So you like there are two ways. You either click here with the middle mouse button on a parameter and you go promote parameter. Or if you want to do all of them, you select like you go VEXVOP options and you go down to, well, I already did it, but there should be a thing that says create input parameters.
Wait, then how do you adjust it after you create the parameter?
You would go up to the higher level. So like I would go back to the OBJ level, and then they're here in the thing here.
Is it
It's here, just one minute, it's here, yeah.
all this stuff?
Yeah.
Roughly the same. Whoa. Who's this?
The the other thing, by the way, is let me do this again. It's good. Like that. Okay, so okay. So here, this is a better version, okay? Like if let's do this one. If I go up and I create a grid, okay? If I go grid, and then I click on the grid and I bring up the rows like this. And then I go into here. If I create, I have to do a couple of things, okay? So I would have to go create turbulent noise. I would have to go turbulent noise, okay? Turbulent noise and displace along normal. Okay. Now the turbulent noise, it takes a bunch of inputs and it needs it's gonna basically a noise function. By the way, the reason I'm doing this stupid noise function in every visual effects artist, like basically all they do is just apply noise to everything over and over and over again. Okay. So like we're not gonna do that as much as they do it, but basically Houdini is just about applying noise to things. Okay. So like what it's doing is there's a noise function. So it needs the keys to source it. So basically like because every position is different, it's generating some function that's different at each point. So it's a function generated from the P's. So you drag the P's in here. Now, the reason it wasn't working before is if you click on this, it's generating a 1D noise. It needs to be changed to a 3D noise. And then this displacement, the noise is the amount and the position is the original position. And then that goes into the displaced position like that. So just try it. By the way, if you go Control B, you can make it big. Yeah, the noise is how much you want to displace it. The P is the original thing that's being displaced. By the way, you don't need to memorize how these nodes get set up. This is just an illustrated example of how VOPS works. Okay, we're not going to be doing this. We're going to be doing very specific things that are related to wind, right? This is just about like how VOPS works. I'm just trying to show you. I want you to do it, okay?
Question.
Yes.
Why did you first plug the geometry directly into the displacement P, but then for turbulent noise, you just do it?
I did it wrong the other.
If you like just now when I directly plugged turbulent noise into P, it just created like
a craziness because it's just setting every P to the value of the turbulent noise.
Oh, it's like random.
It's just setting all the points equal to the turbulent noise function. And this way it's displacing them.
Turbulent noise function creates like the output is a list of like points.
3 points. That's right. It's like it's like an outputting a vector, like a noise vector that it can display.
Then like when you put it into like amount though, it turns into just like a single like number, right? So it's because like it only like displaces it up and down.
Yeah, you're right. So
So
I'm not sure. I think it has to do with the fact that it's calculating the noise function only over the 3-dimensional range. So like it's rather than like a 1D noise, like it won't work because every point is just getting mapped like onto a 1-dimensional function. It's not to do with what I said before. It's not to do with outputting a vector. It's to do with how it kind of the noise function is not completely random. It's like a noise. It's a function. Yeah, and so like it has a sort of regular quality to it. And so it just has to do with the fact that if you have things in a three-dimensionally generated format, that function will map nicely onto the three-dimensional object.
Okay. But somehow when you plug in turbulent noise into amount, it converts.
It's not converting into a vector. I misspoke.
Oh, okay.
It is just a float. It is just a single number. The 3D, 1D has to do with how it's generated. And it's not completely random. It's generated based on its position in 3D space.
Is there a way to check like what type of like is there a way to check like what type of thing the node is outputting, like a type of like
No,
variable? Like
there isn't.
Grasshopper you can check.
No, you can't do that.
Oh, that's
It's
funny.
very frustrating. Yes, you can't just look at the value.
Oh, okay. Let me know like what it is.
Yeah. Okay. So by the way, there's one more thing I want to show you, which is I could do a vector vector to vector 4. And then I could plug the P into this, and I could plug the time into this. And then I believe I can generate the turbulent noise with time as well. And then if I go back to my thing, I believe it will. No, I'm wrong. That didn't work.
What?
Okay. Does anybody have any more questions about this? I'm sure you do, but like you don't need to know how to do this.
Like clarifying question.
Yes.
When you so just now when you're inside this attribute blob, you click into one of these nodes and you're adjusting those things. That's like you're adjusting everything inside here and you save those variables. When you turn it into like a parameter, it will like essentially like place it on the outside and then you can adjust it from there.
Correct. Yeah, I'm promoting. I'm saying taking these things out of this context and letting me adjust them in the parameters. So whenever you look at anything by Houdini, any of those things where you have all those sliders, they're all created this way.
It's just like another like node that links to this and it goes out.
Yeah. So everything in the entire program is created this way.
Exception that promote something to
the higher level. That's right.
Access that thing.
That's right. That's right. That's right. And by the way, I find this confusing, by the way, this whole long list of things. I find it confusing. So usually I would delete these. And what I would do instead is get familiar with the terminology they use. They call it a bind. So basically you bind something and you have to type the name in here. So the name I'm looking for is P. So I just bind the P and then I do a bind export and I export to the P. So P is not a float. P is supposed to be a vector.
That is like locked. Wait, never mind.
I have to say, if I screw this up, I don't.
Vector. No, it's not.
I don't know. I apologize. There are some, by the way, I don't, let's.
It's not, why did it into vector? Oh, over the.
Why is it there's two binds? There's the first bind.
Oh, and then you change it to vector.
Let's just leave it with the standard inputs because I don't, by the way, we're not going to be working in these attributes, okay, like this. It's just this is the way that it works. okay, is we're going to be doing it in a slightly different context. So I just wanna um uh I just want to show you there is this, but I would like to, before we run out of time, also show you like the next concept, which is does anybody need a break, by the way? Okay, let's take a break. We need a break. Okay. All right. We can take like a 15-minute break. Okay. All right.
Yes. Up here is where you start from. Here? Yeah, so you start from this. That's line that's. Just like. Very different. Here, you like right for this one. No, it's different. I mean, that's not good idea. Yeah. Oh,
Yeah.
here for.
I'm curious, does Houdini ever plug into Rhino?
We're going to use Rhino geometry for the collisions. Correct. Yes. Yeah.
But I don't know how to.
Yeah. So, like, zoom out. Zoom out so I can see the whole thing. Yeah. What type of nodes do you have? That looks
Cool and nice.
right. So just zoom out, go back to the next level, and preview the attribute block instead. Yeah, it looks like it's on. It's just very. This needs to go into the first one.
It matters with.
Yeah,
Bubble it's in.
yeah, it does. Now turn this on.
Okay, cool. Okay, so the first one, it's the one. Well, I don't know.
Yeah, it has to go into the first bubble. It doesn't have to, but it's set up to automatically pull things from the first bubble.
We can also get HTML course and do the first one first.
Yes, that's right. That's exactly right. If you go into your thing, like you see those are the other ones. So if you want to access things from the other ones, like you have to do a different kind of a mode. You have to like get a variable in a different way. This is all the exploded version of the first one, and then those are the other ones.
Oh, so this is like the general that you always use.
Yes, that's right. And like, so basically, like, by the way, it's very confusing. Like there's zillions of nodes and zillions of ways of connecting them. And like I screw it up constantly. Like I really do. And but it's a really okay because what we're going to be doing is very specific. And so we just need to get familiar with the methods that we're do of the things that we're trying to do.
Okay. By the way, regarding
Very
the
dangerous.
president, I was thinking, just in case it's possible. I, so I was thinking, I did a project back in Spain, and I was thinking maybe if it's possible to analyze it, so it's this one.
Yes, definitely. This is your own.
Yeah,
Great.
I want to know how it performs with the wind. Perfect. Because I wanted to open a window, but another guy in the studio didn't. And I want to make sure that it will.
That's great.
Okay. So this would be for the wind.
That's perfect. I'm gonna get a snack.
Yes, right.
Yeah.
Take it down. This is
Well, yeah, maybe there. Yeah, you know, it seems like that. He just kind of he understands this so well that he just like
yeah, it's like, I'm like, okay, so it was P with what?
yeah, he's not the best at explaining. This is what my third class I've had with him. And he's just very like
Yeah, you get used to like, because I guess we're gonna do the simulation like tons of times.
Yeah.
So I hope we end up.
I can almost guarantee you he's just gonna send us the pre-built version. He may like walk us through it, but in the end he's just gonna upload it. And then we'll just go.
And then you express. Okay.
It's usually how he rolls.
Well, that makes me feel better. I don't
And if he doesn't ask him for it, I'm fine.
That's great.
Yeah, I don't know. I know, I think it's like maybe common sense.
I think you should like.
No, I know.
Yeah, maybe I'm 30 for.
Yeah.
Why they ask for everything? They should ask for everything.
But up front, I was just like holding the line for a job.
Yeah,
I was like supplying the order.
yeah.
Like there's something really that.
Sounds like this.
Probably. Like no, hang on, important.
I mean, well, these things they schedule an interview and you should be say if I want to go movie like
Yeah.
or
Yeah, because I'm like, after my phone and stuff, right? Like, just they're like starting to interview, like, this is great. Just like, so rare, you know, very one of my favorite. You know, something like that. It's a lot of variety. It's contacts. And then that, instantly, well, it's not like my credit score, I mean, that's okay. Probably not a line. Let's see how much I'm just going to do. I did ask them for more than everything. That's worse. I was like, I want to try that something. I don't know, so like crazy. I didn't really any references. It's so funny. Yeah. It's just I came down, okay, great. I don't bet you economy. Yeah,
The sayings.
And then the green summer, it's like.
And those are the
Exactly. It's like it was built for every day. You start your life.
everyone else.
It's so like a grant.
Like I don't want to.
Yeah, exactly.
Like 3 years.
Like Dawn's front test, I would never put down. I emailed them on Friday. Yeah, I was like, master's one. I emailed them. It's like,
There's just,
well, so
there's something.
I don't know. I don't know anything about that.
Right.
Last minute.
Right. Yeah.
It seems like it's one guy, and that's all the role needs.
How many?
It's.
But
Like, you never like all the
disaggregation.
Yeah.
That's kind of.
Very old school.
Nice.
But
Because. How I know about that.
it's nice.
Residential. It's been nice so far, but it's fascinating. Most things are not going off the bed. And then sexual dreams.
That's
Yeah.
like there's things like
No, I don't. He called it glasses. Yeah. Get that brick.
Yeah.
Yeah.
How are you guys doing?
Virginia is really fun.
That's a good one.
Pretty crazy though. Did you write this from scratch?
This one?
Yeah.
Yeah. So that's what we're gonna do next.
Is Houdini considered ruler or the grand?
It's Eulerian. It's the same exact thing that as mine.
Okay.
The-
How do you like start approach like how do you approach writing the grasshopper thing? Like, did you like look at like
I read the original. I read all the papers.
you just build in those algorithms into the code essentially?
Like I read the Josh Stam paper, and then I read like some books on like fluid simulation, and they're all the same.
But does the C for C sharp like does it have like a visual library that you like import it into, or it's just like
Well, Grasshopper has Rhino has
Import,
a
like,
inbuilt coding language.
okay, so you import that, like like
You use the so I will describe you use the class. So have you ever programmed at all? You know how there's you know what object oriented programming
Yes.
is? You know how there's like classes
Yes.
with properties and methods? So Rhino has like a huge library.
So you just import the Rhino library.
You import the Rhino library and then you use those functionalities. Yeah.
Okay.
But so actually with for the fluids, it's so when you want to do anything that's performance based,
Yeah.
you need to store everything as like basic types. So like you don't actually have any geometry in the simulator. It's
Okay.
literally just like numbers,
Okay.
and then it gets displayed.
Okay.
And so the reason why Houdini is fast is because it's the best at displaying. Because like they have optimized languages for display. They have optimized libraries for displaying large data sets.
Okay.
And so like the displaying is the issue. The simulation is blindingly flat. It's just numbers written it's just lists of numbers getting updated. But then when you want to display that as a point in space, it's very slow.
Briefly, like what is the main difference between like Houdini and like just like other softwares that have like simulation like
I don't know. So
Maya
Maya's the same exactly. The way Houdini works. Well, I don't know everything, but I'm telling you the way that it is written under the hood is identical.
I see.
Like the fundamental aspects of the algorithm,
Right.
not its implementation.
Okay.
It's the way what it is doing. The algorithm is different than the implementation slightly. The implementation has to do with the language and the libraries and the way it's syntax, but the algorithm is identical. And all of this is different than what you get in ANSYS, which is we'll talk about later. This is not ANSYS is for engineering. This Houdini and Maya and everything, and what mine is for visual display. It's for animation. So you can do things that are completely and utterly unrealistic. This is also that is attempt to give you actual real world data. A whole different process, although the simulation is very similar fundamentally.
Right.
It's very similar, although the coding is a little that they don't use boxes. They use like tiny little parcels of space.
Okay. So we're talking like the Eulerian thing. Okay.
It's well, so my like the Eulerian thing, okay, is like the Eulerian thing is like is a bunch of boxes.
Right.
So it's still Eulerian when they're not boxes.
They just
But-
different shapes.
Like ANSYS or SimScale would use weird shaped bubbles of space, and it changes the way you have to write the algorithm because like basically you can no longer like assign velocities so
Right.
clearly to the
no longer follows like a Cartesian like sort of-
yeah. Instead, what you have to do is like you have to calculate like the amount of flux of every quantity going into and out of a cell.
Okay.
So basically, every single one of these parcels of space has like 6 differential equations,
Okay. I see.
and it calculates like the it'll iterate through them all and get an approximate value, and then it'll iterate through them all again and get a better value, and then it'll iterate through them all again until the values hopefully converge. And many times they don't converge. And if they don't converge, like you did something wrong or you have to try again, you know?
Yeah.
So like that is you know, it's a funny thing. I have to say, we should actually talk about it. Is everyone back? Or we should actually talk about it. I like very briefly. I have like I have slightly complex goals in this class. And I have to say, like, I'm not completely 100% confident in the meaning of all of those goals. My goals are several. One is just to give you tools and to expose you to experiences of things that you maybe haven't been exposed to. So I want to expose you to the physical stuff that you haven't been exposed to. I want to expose you to different ways of simulating things. I want to expose you to the language of mathematics. I want to expose you to the language of code. I just want to make sure that you get, like, while you have the few of the classes at the GSD, I want to make sure that you understand the context for varieties of explorations that you might be interested, and that you have the beginnings of the familiarity with those languages to pursue them. Okay, so that seems like enough for me to then, like, if I can do that, then I feel like I have enough leeway to then make a thesis and try to do something together. And my thesis would be that because of the immense entrance fee of using a piece of software like ANSYS or SimScale, no one is actually going to use it like to design with in the way that you would like go down in the wood shop and play around with wood or play around with metal and like make it a part of your design process. And so what I want to do is come up with tools together that we can make environmental forces like part of our design process. And so Houdini and my simulator are not CFD. They are not CFD. And we will talk about CFD later. But they are not CFD. They are CFD. I mean, they are, okay, under the umbrella of CFD. So that word is not precisely applied. But if you're thinking about like the images you see like in a magazine where they have a bunch of arrows flying around and they're analyzing COVID or something like that, that is done in SimScale or ANSYS or you know, like a couple of other packages of software like that. And those are the ones that they break the world down not into cubes. They break the world down into funny shaped parcels, and they do matrix math to calculate the flux out of every cell. Okay, and that is like very slow, and they don't move. They're trying to converge to a single solution through many, 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 many iterations. These tools are for visualizing things like before your eyes, and they're optimized to be run in real time. So you can get simulations of things happening before your eyes. And I think that if we learn enough about the way in which we expect them to operate, and we have access to the tools to do it, that we can get meaningful information out of it. I don't think this is any different than a wind tunnel. It's like a physical wind. It's like a digital wind tunnel. So what I think I want to do is have as many approaches towards the way in which this stuff is simulated right now. So I want to talk to you about the CFD. I want to talk to you about this. I want to talk to you about, you know, the physical models. We'll look at all, and I talked to you the other day about the funny like envelope flow models, and we can get exposed to all of those, and then I think we can make visualizations in this way because nobody's really doing it right now. And I think it maybe will open up a terrain of environmentally interested design work to you in the future. That's sort of my goal. Okay. Does that make sense to everybody? All right. So this runs like that. So that's like a wind tunnel simulation, okay, of a building. And then I also have, let me just show you where we're going. I also have this one, which is like cool air coming in around a heat source and filling up a box. Okay, so in order to do this simulation here, this one, you can see there's a model in there in the middle. So that model is from Rhino, and it is imported this way. So in Rhino I had there it is. Okay, it's like it's just a solid, and it doesn't have to be one shape. They're different. It's just a model with some thickness. Okay. And then you export this as a motion builder FBX. Okay. And then when you export that as an FBX, you need to mesh it, and you need to do this thing where you map Rhino Z to FBXY. So for some reason, most software actually Y is up and not Z. Rhino is like the only one where Z is up. So usually, like you got to do that. You got to map the Z to the Y. Okay. Then if you export that, it'll ask you to mesh it like an STL. And then in Houdini, you can go to the OBJ level here, and you can make a geometry node, and you can call it whatever you want. You can call it like model or whatever. And then you go in there. And I think it's let me see how I did it. You go in here, yeah, it's a file. And then that's the file. And then a transform, which is just to move it around. So like basically you can open this up and use it. This is there's the file. You load it like this. That brings it in. If I just turn this on, it'll look like that. Okay? I don't know why it looks like that. But it'll look like that. And then you can append a transform. And that is that's just to move it around and scale it. So if you have a transform, by the way, everyone will have this problem over and over and over again. Like you always need to turn on the blue thing if you want to see it. If I have a transform, I can move this thing around. And that's how I would position it. And then all of this is something else. Okay, I put a transparent material on it, and I also put a clipping plane on it. So this is like a clip node. This clip node lets you do a clipping plane. And this is when you have numbers here, you can always enter a number. So I could, if it like tops out, you can always enter a bigger number. And if you want to clip in the other direction, it's this up direction that has to be changed. So like if I wanted to go like 0, 1, now it's clipping in that way. So this is like this is a little setup here to import a Rhino model, and I made it clear. We'll go over materials later. Okay, I'm not gonna do that right now, but like this is a little generic material, and that can be changed right here, just like in V-Ray. You know what I mean? It's just the same old shit. So like that is in this material level, and then getting back is sometimes tricky to get back to your context correctly. So I always lose myself, and sometimes I have to okay. In order to make it black, you press D. D brings up the options. Okay, and that is this background dark. And then I always turn off the grid, which is up here too. Like that. So basically, you have a model, you can just use this setup and import a model. And if you imagine a model, like the model is going to be discretized into voxels. Do you guys know what a voxel is? A voxel is a 3D pixel. Okay, so like if I go to my little presentation here that I skipped over too much, like uh a voxel. Okay, so Rhino is a surface-based modeler, but many people are interested in voxels because you can use them to model things that have thickness, like a brain. And so Minecraft is also voxel, okay? So basically, whatever Rhino model you import, if it's like a house like this, it'll be discretized into little voxels, like that. And so the wall thickness is going to have to be thicker than the cell of the voxel simulation, or it won't work. But it's not that touchy. So like I wouldn't, if it doesn't work, you might have to thicken it later, but I think it can be like a normal scale, basically. Okay. So you import a model that way. Okay. And then there are simulators in Houdini, okay, there are many. There are like this is like my little thing here. So there's like this is the OBJ level, and then underneath the OBJ level is the geometry level where you make things, and then there's SOPs, which have transforms and boxes and toruses. Then there's VOPs, which have these attribute things. And then there's DOTs, which are the dynamic solver. Okay, and there are many. There's the pop solver, which is for particles. There's the flip solver, which is for like water, like a surface water. There's the vellum solver, which is for like drapes and cloth. The static solver is for things falling on each other. And for gases, it's called the pyro solver. Okay, and the pyro solver uses gas microsolvers, which are the same things that I have in mind. But Houdini has a sort of a weird thing, which is that the pyro solver is like very popular. So they repackaged it in an easier format within the SOPs context. So it's sort of confusing because it fucks up your understanding of the way the program works, but it's much easier to use. So basically, in order to make a smoke simulation, essentially, what you need to do is you need to create another geometry node. We would call this, smoke simulation. And then you would jump in here and you would just drop a pyro solver. Okay. And then you need to, into the pyro solver, we need to give it sources. So if you look at the pyro solver, this is very confusing. The way it used to work, is you would not do that. You would drop a DOP network. And you would go in here, and inside the DOP network, there would be a pyro solver, a volume source, and a smoke object. Okay, and these would be connected like this. And if you recognize this, it still works this way. It's just hidden. This is the container for all the data. Those are the fields that exist. That's the things that are getting sourced in, and that's the solver that's running all the solutions. So that is like every simulator is that. This is what it is. It's a solver with inputs sourcing to a bunch of fields.
What's the volume source again?
That's the same thing in mind. That's like the collision field and the temperature field and the density field. You're importing original data to start the simulation. All that data gets stored in the smoke object internally, and then the solver just runs on it over and over and over and over and over.
But what's the difference between smoke object and volume source?
Yeah. So if you remember in mine, like there were all these things that we were importing, like the speed and the into the things. And then if you look inside, there were all those arrays that I showed you, like of temperature and density and everything like that. So this is the internal storage of the Pyro solver. And that is the inputs that you generate to get it going. So like basically like you say like you create a temperature field and a density field of smoke to start the simulation. The initial values that you input get placed in long lists that are kept in the memory of the solver. There are two copies of the information. There's a version of the information that you create, and then there's a version of the information that like so like basically like you create a density field, a temperature field, and a velocity field. And then you import those into the density field, the temperature field, and the velocity field in the computer's memory. And then those things are cycled through the solver over and over and over again on every single frame. And sometimes on the update, you can still add new things. So like if you're pumping temperature in, that would be coming from your source temperature. These things are then what you expose when you want to look at it. So like, then you take these internal ones and you put them out. So like, it's oh my gosh, there are always three parts. There is the inputs that you create, the internal storage of the program that then you will expose when you want to display things, and then the solver, and the solver calculates the physics over and over and over again on every single frame. Okay, so I think just like so this is the way it used to be, is it was sort of exposed like this in a very clear way. Now it is all packaged together into a single node that you can just use like alone in the like normally here. Okay. And if we look at it for a second, let's make this big. There is a bunch of things. So there's the voxel size. That's how big the grid is. This is the thing that slows it down. That's the resolution. Then there's the sourcing. So this is the copying of the fields. So this is because density is going to get copied to density, temperature is going to get copied to temperature. Okay, so it's kind of weird, but like this second word is the internal word memory, and this first word is the source that you're supposed to plug in. So like the first thing is like you copy all these fields in, and then if you go to this fields tab, okay, this is about like the internal fields. So it has some information on like the internal very annoying. Has some information on like the internal fields in the thing. Okay, so like you can see there's density, temperature, color, speed, whatever. These are some internal fields, okay? Then at the end, there's the output. Those are the fields that are getting output. Okay, so they're outputting density, temperature. We don't need these, so I will delete flame, velocity, and CD. And instead, we will add pressure. And I can do that because that's the name that Houdini uses for it. I don't know. It just doesn't automatically expose it. Just like my solver, it calculates pressure every frame, and it's in there. You can just expose it. Okay. So, and we could also expose vel, which is the name for velocity. Okay. So these are the fields to export. Maybe we do want speed. I don't know. Okay. Temperature, field, speed, vel. Okay. So voxel size. These are the like render parameters. They're like this is like a rendering engine. Okay. They're like this is like how detailed is the simulation, right? We'll deal with that later. This is the voxel size. This is this import. And then this is the output. Okay. And then there's this shape tab. Okay. And the shape tab has the things that I mentioned. I don't know if you remember, I mentioned them like here at the beginning. I talked about how like basically you source things in, then the velocity moves itself, and then you add turbulence, disturbance, viscosity, buoyancy, vorticity, confinement, all of the parts of a fluid broken down in the way that we have learned to do it over years. And then you do the pressure projection. So like basically, if you go to the shape tab, no. I think I'm in my other one. Here. You go to the shape tab, there's the buoyancy, wind, disturbance, turbulence, shredding, viscosity. These are the micro solvers. These checkboxes correspond to my Boolean that I can turn on and off in my solver. Okay, so like you can uncheck buoyancy and you can turn on wind. And this is like doing the same thing that mine is doing. It's pumping in a velocity every single frame. Although theirs is a little more sophisticated because it behaves like wind. It won't let itself go over a maximum. You know, like it'll like keep adding velocity, but not faster than itself. Okay. So these things are just to make it look nicer. So like if you are a visual effects artist, you always turn on all this shit. And like I find it a little like I probably like would leave most of it off. Maybe one of them, like a little disturbance, that just breaks up the smoke. So it doesn't look like a uniform ball like blowing in one direction. Remember I told you we have no mathematical model for turbulence? So we just in CFD they have empirical models where they just add it in a more accurate way. And in animation software, you just add it in a non-accurate way, just so it looks nice. Okay. So that is that's the Pyro solver, basically. So all we need to do in order to make this work is we need to accurately send in the sources, and then we need to know how to get the sources out and display them, right? Okay, so in order to send in the sources, we Houdini, all that stuff we were doing with the VOP, with the attribute VOP and everything, all of that is for, like the things I showed you with like the torus that have points on them. We're not working with points anymore, we're working with voxels, right? So in simulation solve voxels. So we need to make what Houdini calls volumes or VDBs. There are two kinds. volumes and VDBs. VDBs are like they're what's called sparse volumes. So a volume is like all of space is discretized into cubes, into voxels, and a sparse volume, a VDB is a sparse volume, meaning it only keeps the ones that where there's data. So it's like a more efficient version of a volume. And that's very good for animation if you just want to display some smoke. But unfortunately, it's not very good for us since we want to get like speed and pressure information all throughout the whole simulation. So we have to hack it to make. We either have to use the old version where they didn't have the sparse solver, or we have to hack it so it doesn't use its sparse solver. So what I always do is I go into the setup here. I've tried to use both, and I think that it will be more confusing to use the legacy version. So I think we should use this version. And what I do is I go into the setup and I turn off the sparse solver. I turn it to dense so that it calculates all the values. And then I also give it a maximum bound so it doesn't expand infinitely. I give it like, some sort of maximum bounds. Okay. All right. So in order to make a volume, there are a couple of ways. So, like one way is I'm just going to make a sphere, okay? And then I'm going to do a volume. I'm going to do a VDB from polygon. And that, if I display this, you'll see, let me turn off my, that will create this, okay? So this, if you do a VDB from polygon, it converts just a shape into a voxel geometry, okay? But it's doing there's this thing up here called distance VDB, and that means that is converting it into what's called an SDF, or a signed distance field. So there are two kinds of VDBs. One is for collisions, that's the signed distance field, and the other is a fog. So this is for collisions, this is for sources. So again, the principle is you need a volumetric source, and you need for collisions a signed distance field. And so the signed distance field is this distance VDB, and the volumetric source would be like this fog VDB. It's like a voxel database or something like that. Voxel density, I don't know. Let's look it up. Volumetric dynamic grid. So this needs to have the name density in order to be sourced correctly into the density. And you can change these names. You can call them whatever you want. You can call it, like clam chowder or whatever. It doesn't matter, okay? But like this is an attribute, a field that is attached to this object. Okay, so like this is typically called density, and then I would pump that into the pyro solver, into the first node of the pyro solver, and I would go in the pyro solver to sourcing, and I would check that my density is being sourced into my density. Okay, and for now, I'm gonna turn off, val, turn off flame, and turn off temperature. All I really need for a simulation is density. Not enough sources specified. And then, you can see it's just like, I don't know, sourcing in some density.
You just click play and it starts working.
Yeah. And I can explain why that's working and how it's working, but basically what it's doing is it's just sourcing in some density. And the reason it's on is because this wind is kind of on by default, and so is the disturbance. Okay. So if I like crank this wind up, it's going to go faster. If I crank the disturbance up, and you can see it's getting cut off here. It's getting cut off here because I set it some bounds. If I didn't have the bounds, it would just keep expanding infinitely and infinitely until my computer crashed. Okay. So if I turn these off, it is just going to sit here and gradually build up density in that one spot. And then sometimes instead of doing this VDB from Polygon, people will do, I think, what's called uh, um, a different way of creating the VDB, okay, which is, well, actually, maybe I should not confuse matters right now. There's other ways of making these volumes that you would make them in that would be useful in different contexts. You don't make every volume this way. This is just the simplest way. Okay. So and you don't always use the microsolver. Sometimes you create your own wind like dynamically rather than just turning on this wind button. Okay. Then if I wanna make a collision, okay, I'm gonna make a box. Make a box over here. Like that. And I'm gonna click on this box, and I'm gonna do another. I'm gonna make a transform like that. And then I'll turn that on. And if I want to see the other simulation, I need to go over here and check this little pink thing, which is the template, so I can see where my source is while I'm moving the other thing. So then over here, I can make this box. I can make it, bigger. And then I can go over here and I can hit enter and I can move it over here. I'm going to make it skinnier. Okay. And then that needs another VDB from Polygon. Only this one is going to be the distance VDB because this is my collider. And let's imagine that I had two of these. Let's imagine I copy this. I'm going to copy this over. and I'm gonna make another box, you know, like uh here. Okay, and I'm gonna move that box here or something. Okay. Then I'm gonna do a merge. And I'll merge the two of them before I convert them into this VDB. And if I click on this VDB, I've got these two like little wally things. Okay. So merge is a little more flexible than it is in like Grasshopper. In Grasshopper, like merge means something very specific. Here, what it's doing is it's just like those two things are becoming one, sort of. Although I need to convert them into a VDB afterward, because otherwise I would have to like merge the voxels in a more complicated way. Okay, so if I click on here, this is called surface. That's the name of the VDB that it created. And it used the voxel size, you can see. So I could change this. I could make it bigger or smaller. And I'm not sure, honestly, if this matters, but I often check fill interior. Collisions are sometimes a little finicky, okay? And then I'm going to pull that VDB into the collision geometry volumes over here. And I'm going to go in my PyroSolver to the collision tab. And instead of using this collision geometry, which I think works on just geometry rather than the sign distance field, I'm going to use the SDF plus volume velocity. And that, instead of saying collision, this needs to read surface. That stands for sign distance field plus volume velocity. Yes, I went to so I pulled the VDB from Polygon into the PyroSolver on the other side, and then I went to the collision tab in the PyroSolver and changed this to SDF plus volume velocity.
What's the purpose of doing? What is the difference?
It works a little better, honestly. But the other reason is if you had a moving piece of geometry, this is the only one that works. Because the way, actually, it's very interesting. The way you simulate moving collisions with fluid dynamics is like you give every piece of the surface on its inside like a velocity, and then like the velocity gets actually picked up by basically it's inputting velocity into the simulation. Okay, so I don't know. We could use the other one too, but then if you were using the other one, it wouldn't be this way. It would instead be just the merge that would go in. Does that make sense? And then if I go to my PyroSolver and I click on the display and I start it over again, I mean, it's hitting the wall. It doesn't look very impressive, but you can see it's hitting the invisible wall. I often like just turn on my smooth shaded, and if you hit escape and you have to turn off all these pink things, you can see just the thing.
What is the difference between the pink viewer and the blue viewer?
The blue viewer is the thing that is being like the dominant preview. The pink viewer is a template just to see like what's there. Yeah. So if you want to see both, that's typically not what you would do. But you would typically just use this as a guide. Like I typically just turn it on as a guide like that. If you want to see both in the output, you need to do another merge and merge the pyrosolver with the original box geometry, and then you can turn on the display for that.
Allows you to see like one thing at
Only allowed to see one thing at a time. And then if we go to the pyrosolver, if we go to this shape tab, is it not for you? Let's wait. Who is it working for and who is it not? Does anyone need help? You don't have any flow. Let me see your thing. So you need to polygon, click on that. You need to click on the blue thing to see it. Yeah, and this is not, this is still the distance DVD. So you need to convert it to a fog DVD. Okay, and then you can check that. And now it's a fog DVD, and then you go in here. And then sort of sourcing. You've got density going to density. And
It's not colliding
since you don't have.
I'll tell you this one.
Yep.
It's not colliding from Mars.
And then you go up to the top, and you go to the shape tab. You have wind, you can turn off wind.
Why is yours way smoother than mine?
And then if you shake on the blue
Why,
shape,
that's, I think I can.
Why is yours
wire. Maybe.
Like this.
Yeah. You go to
higher?
And then I think you still have the
service.
wire thing on.
The mine looks really like fake.
Yeah. And then if you play the
It's on
pyro.
super low res. It's
Yeah.
so smooth.
Back. That's playing back.
Why does it even state the FPS? With yours?
That is FPS.
Your wind is hitting the bound.
No.
Of the container.
I don't have the.
Or it's dissipating very quickly.
Okay, but how do you get it to mine is not colliding at all?
I think
Yeah.
it's just experiments.
Yeah, so you can change
Not
it,
colliding.
It's like.
for the negative number. The wind, if you
Yeah, it's
download the
basically.
tab,
It's like this is the. this is the
Wow.
necklace.
you change the direction.
There's not.
Does anybody need help?
This,
Yeah.
This?
All these like white
it's not collision.
boxes.
Yeah.
Look, it's not showing like.
So,
Is that just? Yeah.
That's just a display. So that boundary box is the boundary of the volume.
Shoot, it's flash.
Like the volume is taking up that space, but it's not,
Oh,
it
no,
doesn't
it's
have
working.
data
Yeah,
there.
on it, it's like, okay.
Yeah, that's because you're using the sparse solver, so it's like dynamically
Go to-
resizing to where there's data.
Go to the
So if you just,
pyrosolver.
I think if you type Shift W, or if you just go up here
Oh, it does work.
to the
Yeah.
first one,
It does.
yeah.
Yeah,
Go
go
to,
to.
yeah,
I think
like
it's sourcing.
that,
No,
yeah.
it's collision.
And you just go to shape,
It's
smooth
change
shape.
the collision SDF to surface.
And then also you need to turn off.
Right again.
Oh, oh, oh.
That works.
That thing.
I can move my
I missed-
boxes.
I missed
I think if you hit escape, Yeah.
Oh, maybe.
Wait, what? Wait, what?
Yeah. Okay, so she's-
Oh, other question. Why do you need it to a collision SDF? You need to change it to a surface or it won't work. Yeah.
Okay, so that is very important. What you just asked, the surface is not, it's not saying that it's a surface. That's the name of the field.
Oh,
So like you can name it anything that you want, but then when you source it into if you go to the pyrosolver, like if you go to your collisions tab, yeah, so it's looking for a surface. So let's see what you named this. You named it surface.
so if I do like dog.
Yeah, then you need to change the pyro to be, it won't
Oh, now it
collide
won't collide.
unless you change it to be dog in the pyrosolver.
Interesting. Oh, but I did do dog. Now it's no longer working.
Well, they both have to have the same name.
Oh,
Then collision, right?
It's the, in the collision,
this has to be dog. This
that has to be dog.
this is the.
Yeah, they both have, the source and the destination have to have the same name.
So now it should work, right?
Yeah,
Choose.
yes, it is in fact, very similar. To moving around the blocks of the,
Oh, now it's working.
of the, you know, simulation. Like basically there's a little parameter for every single part of a simulator.
What's it do? Let's shift W do. Oh,
Yeah,
yeah,
you
Congo's
cannot
got
see the
wire.
wall ever. The wall is not there.
Yeah.
How does?
So the way that I'm doing it there is not a good way to do it.
Oh,
Like this is not something you should do. Like what I did here, okay, is what I did here is I used a merge here. See, I merged the fog with the original box. But that's not the way we're going to do it, okay? Because what you're going to do is you're going to import a Rhino model, and you'll bring it in here. So, we can do that in a. You would never have the collider. Like right now, I have the collider inside of the smoke simulation. It's kind of a backwards way of doing it, right? Like what I should do is build the collider up a level and import it into the smoke simulation. So like what I can do instead, okay, is I can do an object merge. And I can click here and it'll bring up my tree view. And you guys don't have this, but I can go find my context model. The object merge is like it's just this button right here. This is like the import button.
oh, okay.
So that's how like you can import your Rhino model. So let's do it let's make just I'm gonna do it without a Rhino model for now. So let's let's if I go back, okay, up a level, if I go back to the object level here, if I just like if I go to I copy these boxes that I created, I go up and then I make another thing, which I'm gonna call this collider. I'm gonna paste them in here. And then in my smoke simulation, I can go object merge, collider, and I can bring that into the BDB from Polygon.
Is there a reason why you have the BDB from Polygon here and not in the other place, and then you can just direct?
Yeah, there is because up here I want to see it as its original self. Like this model up here, I want to be.
You don't want to see the box line version.
Yeah. And by the way, there's one more thing I would have to do, which is here I would have to merge these. And then I usually create a null. And I would call this like collider out. Everyone in Houdini always ends things with nulls. The null is just like an operation that's doing nothing. So you use that to like make names. So like you can make a collider here. In its own context.
If you have like multiple nodes inside collider. Like how does it know to import the thing you want? Or you kind of multiple.
I didn't select, I selected the collider name as in the object merge. Like in the object merge, I went over here. I I selected, it opens my entire tree. And I just selected the thing that I had named. And it will select the last thing. It'll select whatever has the blue tag on it.
Oh, okay, that's okay. So if you change the blue tag to something else.
That's the dominant thing. That's what it exists.
So now we'll automatically just take whatever it is.
Whatever's blue tagged is the thing that's exported.
Now it's just to name it, that's all.
The blue tag is the thing that is getting exported from a context.
How do I, which node do you use to call back the polygons that we just put, the VEBs that we just put in the other, like the object?
This thing, this is just, it's just called an object merge. And then actually, so this is very helpful, by the way. If you see the things that it says on the screen, if you type those, like if I give you a screenshot, if you type what it says on the screen, it'll be the thing. So that's all it takes to blow smoke through some things. Okay? You just need a source of smoke and a pyro solver and an object. And basically, it's a tiny little wind tunnel. Now, I don't know that that really is realistic. I don't know that it looks like the way the wind is behaving. I think in order to get it to behave in a way that is sort of physically reasonable, we will have to do more work than that. We'll have to look at how it's behaving and think about the wind speed and the scale of the object and how much disturbance we want to put into it in order to get it to kind of give us something that looks correct. But basically, that's what it takes. Okay. And I have to say this is a little like a little frustrating for me. Like, you know, the way the Pyro Solver is packaged, I find to be slightly confusing. It hides too much of the internal workings for my tastes. So like it's possible to build these things from scratch, like with like the lower order nodes. And it would be much simpler than this because we wouldn't need all these hundreds of thousands of options. Like the reason it looks like that when you open up the thing is because they're trying to make a network that has millions of checkboxes. So there's all these switches and options and promoted parameters and things like that. But if we were doing it, all we would do is we would say we would just we would just have advect, buoyancy, wind, just the same way, like it would just be the basic algorithm that exists all the time in every single, like this, all of this is unnecessary. This is in order to make it a tool. It's not what's needed in order to run like the thing conceptually. It's because they're making all these checkboxes and options and sliders and because I said allow editing of contents. If you right click on it, you can go allow editing of contents, and then you can it expose the internal workings.
Oh, unlocks it. Okay.
Yeah, and then you can go in here and edit it. Well, yeah, but if you were going to do that, like you wouldn't do this. You would just like well, by the way, even the legacy one has things that are like this is the legacy one inside of the other one. There's the legacy one. So but if you look at this, if you look at it, it has here it is. Here's the, let me see if I can find the real shit.
Wait, how do you expand this window to pick up the whole thing?
Control B. Okay, so let's see if we can look at this a little bit more for one more second here. So if I go to my fields here, and you see there's this dissipation. If I turn off the dissipation, it's gonna like, no. It's gonna like be continuous. Okay. And then the other thing that is frustrating has to do with the fact that, let me see if I can get this collider nearer. Oh, and I need to fix my object merge. Did you see it wasn't colliding because I didn't have the last merge node on. Okay, so if I play this now, yeah, it'll spread out and try to flow around the VDB version of the thing. But if you look at it, there's some issues. There's some issues you can see that have to do with the resolution and also with the way that you can see some sort of breaking up of the source, right? Like you can see some sort of staggering that's happening. So if you go to the setup over here and you expand the simulation, that has to do with the substeps, which is basically the delta t. It's how many steps it's taking per frame. Okay, so like if I bring up the sub steps to something higher and the minimum sub steps to something higher, and then I play this, it will be a lot slower. And it will do a better job colliding, hopefully.
Does a sub-step divide delta t by that number?
Yeah. So like you can see the collision is much more effective. It's sort of spreading out around the object in a more convincing way. And then the other thing, obviously, that affects this is the voxel size. So if you lower the voxel size, you get a higher resolution, but it's even slower, right? So I could go like 0.05 or something. Okay, and it's very slow. You can see it's no longer running in real time, right? And so in order to deal with that, what you can do is you can do a file cache. And before you file cache, we should look at this and we should go to our output and we should check that temperature, speed, Vel, pressure, density, that we're outputting the right things. Then you can put the PyroSolver into the file cache. And if you click on the file cache, you can click this save to disk. And basically, uh, it will pre-bake the simulation, and then you can play it in real time when it's done doing that.
That's the
And
disturbance.
I think, by the way, I think we're out of time. So like you don't have to stay here and do Houdini with me for the next 2 hours. I can stay a little bit, but I did it in the solver setup. Anyway, the reason that what the point there's the min steps and max steps in the solver setup. Um, what I wanted to do today is just to give you the information that you would need to know how to make a Rhino model of a thing and sort of what level of detail you're looking at, and also give you the things that you would need to blow wind through a thing. So now you can blow wind through a thing in Houdini, and you can blow wind through a thing in Rhino. So you can import your model. I'll upload these files so you could import it into my file, and it would just be there. Okay. And that's fine. I know some of you have asked me like when I was holding office hours, and last week was very hectic for me, but this week is not. So I will schedule some things this week, and we can meet about any of these things. And my hope is that like I think I have a lot of more presentations to give you still. I think I need to go give you more presentations on Houdini. I need to give you the presentations on the mathematics behind my code. But I'm also hoping that towards the end we can transition into like I can work with you on getting your simulations to like work the way you want them to work, rather than just talking. So I think you should try something and see how frustrating and horrible it is, and then we can work on it together to get it to be like what you want it to look like. And the other thing is, I don't know that everyone should like like I'll show you like something like, by the way, one other thing before we go. You can also uh let me stop this. You can also, like I showed you, you can color the simulations and have them display temperature and have them display all sorts of things like that. And you can also, by the way, um uh you can have I deleted it. You can have them advect particles as well. So you can make like particle trails that are advected by the smoke. We can hide the smoke. We can have it display pressure and temperature. Like you can do like, like, uh, instead, okay. So like, we can do all sorts of versions of what this should look like. So that's something that like you know uh um like I'm also we can cut slices through it and have it show just a solid thing with the velocities. There's many different versions of it. It's not going to probably look like a smoke blown through a thing. It's just like the simulation setup, not the way we want it to look. So we'll go over that in more detail next time, but that's something that I want to work with you on as well so that you can sort of make it express the things that you're wanting to express. Okay? Questions? You guys want to see the um I'll show you one other thing. Everyone's here. Like I don't know what that's doing it on, but it's like there we go. That's like similar to my simulation, right? It's displaying like a slice of the velocity field. Okay, lots of different different things.
So do you have like a database of like all the records that it has, or you can like look at them? Or like do those?
There's like about 1 million people online recording video tutorials, but I find them, if I'm being honest, like a little hard to follow because they're basically all just trying to make explosions. And so like there is like I think there is like if I look up Pyro solver like this thing here, there's a database here where it like explains things. Okay. I will schedule office hours this week. You guys know what you do. Right?
Other question.
Yeah.
After my file cache loaded, it doesn't work. It stops working.
You got to preview the file. Click on the blue thing on
Oh,
the file.
I did do that. It doesn't. It's like nothing happens.
Let me see it.
I didn't stick. I clicked play. Nothing happened. But it used to work like perfectly. Like even when I do this, I don't know what happened.
Nothing broke.
Yeah. I think it's it may be.
I will know.
It's because I
Did you let it finish the file cache?
I did because I turned the box side to one. Maybe that's why I didn't. I made it. Like, it used to be like one.
One is pretty big.
I wanted it to load quick.
I think one is too,
That's my
too
okay,
big.
probably.
Yeah.
Okay. Okay.
Yeah.
Thank you.